Okay, hi. My name is Michael Kepler. I'm a first-year graduate student in the Electrical and Computer Engineering department. My research area is robotics and control, and I'm currently working on a project with the Navy where we're trying to design a small autonomous underwater vehicle to tow a very, very large rope and guide that rope into the propeller of a ship so that we can stop it. So, yeah. So with all this in mind, I'm pleased to introduce Dr. Stilwell. Dr. Stilwell is a professor in the Electrical and Computer Engineering department. He received his master's in electrical engineering from Virginia Tech, and he received his PhD from Johns Hopkins University. His research addresses autonomy and marine robotics. Dr. Stilwell is the recipient of the NSF Career Award, as well as the Office of Naval Research Young Investigator Award. And with that, I would like to pass things over to Dr. Stilwell.
Thank you very much. Well, I'm delighted to have an opportunity to tell you about how Virginia Tech plans to win the Ocean XPRIZE. Now, the first thing you need is confidence, so check, we've got that. Let me tell you a little bit about XPRIZes. So this light is really bright. XPRIZes are large transformational challenges. Usually there's a dollar award that goes with them. This particular XPRIZE is a $7 million award. All of them ask us to do something that isn't a small step, isn't a little bit of engineering, but something that fundamentally hasn't been done before, something that's a benefit. The very first XPRIZE was the Anasani XPRIZE, and some of you know this. This is the XPRIZE that was about going to space in a reusable spacecraft. Burt Rutan won this, a few of you may know this, in a company called Scaled Composites. And that was the beginning of the commercial spaceflight industry. So this was a really big deal. This change was this fundamental inflection point where it changes an industry. It changes how we do something. The Ocean XPRIZE is about surveying the deep ocean very, very fast. So let me give you the stats of what we're asked to do. In the fall of 2007, can you guys help with this? Fall of 2017, that's this fall, we're going to develop a system, deploy it. It will survey the deep ocean, generate a map at 2,000 meters deep. We've got to do at least 100 square kilometers. While we're down there, we have to find and image things of interest, archaeological, geological things that might be down there. And then a year later, we have to do the same thing again, but twice as deep, 4,000 meters deep. That's 4 kilometers down into the ocean. And we have to do 500 square kilometers in 24 hours. This is orders of magnitude faster than any system we might have today. So let me give you a sense of why this is hard, and let me assure you this is very, very hard. Right now, what the XPRIZE Foundation likes to say, and others say it as well, is that we have sort of understand, we have explored about 5% of our oceans. Now that's a little bit of hyperbole. We actually know a little bit more than that, but not much. What I can say without any hyperbole at all is that we have maps of the entire ocean, but they're just not very good maps, so that they're at a scale of about 5 kilometers. So anything that's smaller than 5 kilometers, we have no idea it's there. We just have nothing. So the vast majority of the ocean, we simply don't know what's down there. If it's a mountain range, we know about that. But anything much smaller, it's a mystery to us. So why is the ocean so hard? Well, to put that in perspective, we can build maps of other places, and it's easier than the ocean. We have much better maps of the moon than we do of our own oceans. We have much better maps of Mars and even Venus than we do of our own oceans. So building a map of the deep ocean is hard. The technology for getting to the deep ocean is very hard as well. Let me put that in perspective. We've been able to put more people on the moon than on the bottom of the ocean. So this is a very challenging problem. All right, so this is the problem. Now let me show you how we're going to solve it. We believe the solution for this type of problem is teams of autonomous underwater vehicles. They're very smart, they can collaborate, and they are individually very expensive. So this is deep ocean subsea swarms of vehicles. We believe that the XPRIZE Foundation is incentivizing us to develop this sort of technology. So what do you have to do to build some science fiction stuff like this? Well, let me give you a list, and I'm going to have to use a really small font because there's a lot of things you have to be good at. You've got to know something about underwater vehicle design. You have to know about propulsion and design and optimization, hydrodynamic analysis, advanced guidance and control, autonomy, both theory and practice, collaborative control of multiple robots, search theory, how do we find things, especially for subsea applications, acoustic communications, that's how our robots will collaborate. And not just at a laboratory scale, but you have to have done this at sea because there's a really big difference between doing it in the laboratory and doing it at sea. Well, it turns out Virginia Tech has, in this country, a unique program in marine autonomy and robotics. We've done all of this, and there's really no place else that has. So as we're looking at how we want to solve this problem and looking at our potential competition, we believe we are solving it. Let me give you, really briefly show you some of the stuff we build. The Navy asked us to build an underwater vehicle that could moor itself on the seafloor. What happened here is a false nose that was held on by a vacuum is released, and it's real simple. We just release the vacuum, falls off, and that becomes an anchor. So now this vehicle can moor itself on the seafloor. We think this is what we're really good at Virginia Tech, which is really simple solution possible. In this case, the vehicle will be underwater for up to a year. It will release that mooring line when it's done, come to the surface. It's got SATCOM, so it'll phone home and ask if anything's changed in the last year, and then it will go off to wherever it's been programmed or told to be picked up. All right. Well, we've done an awful lot of vehicle designs that look like this, and some of the things we need for the XPRIZE, we are actually pulling off the shelf. This is one of our vehicles. This place is about 100 pounds, about 5 feet long. A version of it is outside. It's got when we designed this, we had to solve a particular problem, and to do that, we came up with a tail system that turned out to be full ocean depth. So the stuff on the right here, called a pressure compensated tail, already goes to 4,000 meters. In fact, it'll go to the bottom of the ocean. It'll still work. Our students know all the other stuff too, battery systems for these vehicles, how to use RF in such a way that when we get to the surface, everything will still work again, how to package electronics, what kind of software works, and fundamentally, what are the algorithms that make these vehicles autonomous? How are they going to work reliably without human intervention? All right, so that's our solution. Let me show you exactly where we are right now. So in order to do this, we are coming up with a solution that's using very small, very low-cost underwater vehicles. We have to innovate in navigation. That's answering the question, how do underwater robots know where they are? And we have to innovate in collaborative autonomy. How are these robots going to work together effectively without any humans in the loop? We have designed a low-cost underwater vehicle, and we are building it right now. This is the Javelin AUV. Now, we could buy a vehicle that can go to the deep ocean right now. It would displace several tons. It would require full-time support from a large ship, and it would cost millions and millions and millions of dollars. There's maybe 3 of them in the world. Our solution displaces only 200 pounds, and we can build it, including the sensors we have to buy, for $120K. This is transformative. This fundamentally changes the class of solutions we can consider. So where are we right now? Well, our students are designing and building at light speed, getting ready for the contest this fall, and we're fundraising like crazy. And questions about this?